In this problem, a long nichrome wire with resistance per unit length lambda is bent at right angles at points P and Q to form horizontal conducting rails a distance L apart. This wire is in a magnetic field that's constant, and we have a conducting rod that's aligned with PQ when t equals 0. And this rod is sliding to the right at a constant velocity. So we're asked first to indicate the direction of the current that's induced in the circuit. The easiest way to answer this question is to apply Lenz's law. We see that the rod with the rails form a loop, and there's a magnetic field passing through the center of that loop. And so that means that there's a magnetic flux into the board through that loop. For a constant magnetic field that's perpendicular to the plane of the loop, the magnetic flux through the center of the loop is the magnetic field times the area. And Lenz's law says that if the flux through this loop changes, then a current will be induced that creates its own magnetic field that will try and cancel out that change. So we can see that as this rod slides farther along, the area that we have is larger. That means that the magnetic flux into the page is going to be getting bigger. And so Lenz's law says that there's going to be a current that's induced that will create a magnetic field that's out of the page to try and cancel out that increase in flux into the page. And so using the right-hand rule to find the direction of the magnetic field due to a current, if we want the current through the center of the loop to be pointing out of the page, that would mean that in this rod, the current would need to be going up. In the top, it would need to be going to the left. And so this would be a counterclockwise current. And so the justification for why the induced current must be counterclockwise is exactly what we had said with Lenz's law. There's an increasing magnetic flux into the page, and so the current that's produced creates a magnetic field that's out of the page to try and cancel out that change in flux. One other way that we could have looked at this is because the rod has positive charges inside of it, as those positive charges move to the right, we could apply the magnetic force equation. The magnetic force on a moving charge is the charge times the velocity times the magnetic field. And using the right-hand rule, we could see that the force on positive charge carriers in that conducting rod would be upward, which again, that would produce a current that would be flowing counterclockwise. And so for the next part, we're asked to derive an expression for the magnitude of the induced current as a function of time. And so you can see that I've drawn the area of the loop. It has a height L, and the width of it is x. And so the magnetic flux into the page is going to be B times L times x. Faraday's law says that the induced voltage is going to be equal to the rate of change of that magnetic flux. Again, here we're looking for the magnitude of the voltage that's induced, the magnitude of the induced EMF. Faraday's law on the AP formula sheet says that the induced EMF equals negative the derivative of magnetic flux with respect to time. That negative sign just means that it's trying to cancel out the changing flux. And so here we've already determined what direction the current flows, and so now all we're interested in is how large the induced EMF is. So if we substitute in our magnetic flux, B times L times x, if we take the derivative of that, B and L are constant, so this becomes B times L times dx dt. And dx dt is the velocity of the rod, so this becomes B times L times V. We're trying to find the induced current, and so using Ohm's law, the current equals the voltage divided by the resistance. But as this rod slides along, this nichrome wire, the conducting rails, are getting longer and longer and longer, and they have a resistance that depends on their length. And so we need to find the length of wire that we have so we can find the resistance. And so the length of the nichrome wire that we have is x plus L plus x. And so the total resistance is going to be the resistance per unit length lambda times that total length of L plus 2x. We are interested in how this resistance is changing with time, and so x starts off at 0 when t equals 0. Because this rod is traveling at a constant velocity, the distance x equals the velocity times the time. And so if we substitute that in, we get that the resistance equals lambda times L plus 2 times Vt. And so if I substitute in my voltage and my resistance, I get that my induced current equals BLV divided by lambda times the quantity L plus 2 Vt. Again, this is giving me the current as a function of time. When t equals 0, then that denominator is just lambda times L. And as t gets bigger and bigger and bigger, that denominator is getting bigger. And so that means that there's more resistance, which means that the induced current is going to be getting smaller. In part C, we're asked to derive an expression for the magnitude of the magnetic force on the rod as a function of time. And so this rod has a current flowing in it. And so the magnetic force on a current carrying wire or a current carrying rod is ILB. And so to find the force as a function of time, all we need to do is substitute in our current as a function of time that we found in part B. So we have the current BLV divided by lambda times L plus 2 Vt. We have that current times BL. And so we can multiply that through and we get B squared L squared V divided by lambda times the quantity L plus 2 Vt. And that's our force as a function of time. In part D, we're asked to sketch a graph of the external force as a function of time that must be applied to the rod to keep it moving at a constant speed while in the field. And so if we look back at our diagram, we have the magnetic force that we calculated in part C that's acting to the left. And if this is moving with a constant velocity, there must be a force acting to the right so that the net force is 0. So that external force must be the exact same size as the magnetic force so that the net force is 0, and this will continue at a constant velocity. So the graph of our external force as a function of time is just going to be a graph of the magnetic force as a function of time. As time goes on, the magnetic force gets weaker and weaker and weaker because the current is getting smaller. And so the external force needs to get smaller and smaller to keep this moving at a constant velocity. When t equals 0, the magnetic force is B squared L squared V divided by lambda L. Or because we have L squared divided by L, we can simplify that to B squared L V divided by lambda. And so the external force starts off at that value, and as time goes on, that force is going to get smaller and smaller and smaller, and as t approaches infinity, that magnetic force would approach 0. The final part says that the force pulling the rod is now removed. Indicate whether the speed of the rod will increase, decrease, or remain the same. So again, going back to the drawing, if the external force goes away, we see that we still have the magnetic force that's acting on it. And so that magnetic force will now make the rod accelerate, and the acceleration is opposite the direction of the velocity. And so when the acceleration and the velocity vectors are in opposite directions, that's going to be causing the object to slow down. So this magnetic force will slow the rod down as time goes on, and eventually it would stop. So the answer is that the speed of the rod will decrease because there's now an unbalanced force that causes an acceleration opposite the direction of the velocity. And if the acceleration and the velocity vectors are opposite, the speed must decrease. And that's the end of the problem. Again, this problem involves a little bit of induced EMF. It also involves understanding magnetic force on a current carrying wire. And it also has a little bit of Newton's laws, understanding that if something is moving at a constant velocity, the net force must be 0. So the external force balances the magnetic force. And then understanding that if the external force goes away and we're left with an unbalanced force, that will cause the object to accelerate. And it's understanding that the acceleration and the velocity vectors, if they point in the same direction, an object speeds up. If they point in opposite directions, the object slows down. And so this is a good problem to look at as you're reviewing because it involves induced EMF and magnetic forces, which are two key things that often get asked about in the magnetism questions on the AP test.